This is Big Picture Anatomy with a look at a few different aspects of the mechanics of a movement. We're going to start out by looking how at the mid-range length of a muscle we get maximum force because of what is happening inside the sarcomeres at the molecular level. We're going to look at three different lengths of the bicep muscle as the elbow flexes and see how the changes inside the muscle cells in the sarcomeres at the molecular level affects how much force is actually generated. Let's start with the elbow straight, with the arm almost straight, the elbow at 135 degrees or more, and the biceps muscle stretched out such that there's little overlap between the myosin thick filament and the actin thin filament, resulting in very few cross bridges. Remember, the cross bridges generate force as they row in or pull in on the actin from either side. Because we have the sliding filaments stretched out, low overlap between we have a few number of cross bridges in the open or 135 degree elbow. The result is a relatively low force in a stretched out muscle. If we then bend up the elbow to about 90 degrees, now we see that we have almost perfect overlap between the actin and the myosin, so that all of the available cross bridges are able to form and generate force on both sides of the sarcomere, rowing that in at full force. So the sliding filaments are ideal in their overlap. We have a lot of cross bridge formation at this mid-range or 90-degree length for the muscle, and so we have a high force in that mid-range muscle. Finally, if we bend the elbow yet further and bunch up the muscle, now the actins interfere with each other. They overlap so much that they do not have contact with the thick filament myosin down the middle. And the result is we have a smaller number of cross bridges forming, meaning that there's less little rowers rowing in because they have to row in only on their respective side. And so the actin from each side of the sarcomere overlaps, resulting in interference on the cross bridges. And we have lower force in what is now a bunched up muscle in a flexed or 45-degree elbow. So just to review, as we go from a stretched muscle to a mid-range muscle to a lengthier muscle, we go from not so much cross-bridge formation to ideal cross-bridge formation to, again, interference in cross-bridge formation, and the result is we get the highest level of force from our sarcomeres in a mid-range muscle. Less force when the muscle is stretched out, less force when the muscle is bunched together. Okay, now we want to take a look at how we get different levels of force in a muscle, even no matter what the length of the muscle is. In other words, how do we control the overall force that the muscle generates, whatever length it is at? And we cannot do that by changing what's going on in the sarcomeres, because once a motor unit is active, it's giving everything it's got. What we want to do is compare the difference on the left side here when we're generating low force to lift a weight of only 1 pound as we flex our elbow, compared to the high force we need when we're lifting a weight of, let's say, 20 pounds under the same action as we flex the elbow. And the only difference is that for a low force generation, a very small number of motor neurons in the ventral horn of the spinal cord go to a small number of muscle cells, resulting in a small force. Whereas over here, a lot, maybe almost all of the motor units are active, going to almost all of the muscle cells to lift a very heavy weight, like 20 pounds, as we lift the weight. Of course, we're still, according to our sarcomere actin-myosin overlap, going to get the maximum amount of force at mid-range, but we're trying to get the most force possible at every length of the muscle as we go through the full range of motion, from stretched to as we just flex our elbow, from straight to flexed. So just to review, to get a low amount of force, a small number of motor units are active, causing only a small number of muscle cells to fire or to be activated as we flex our elbow, whereas for high force, we have a lot of motor units active, causing many or almost all of the muscle cells to be active as we flex our elbow. Now, because of the way the sarcomeres are lined up along the length of the muscle, and as they shorten, they can generate force for a lengthening distance of about 20% of the muscle length. And because of the way we get more force with more motor units, our muscle architecture changes depending on what a particular muscle has to do. Sometimes we need long, skinny muscles with a lot of sarcomeres and muscle cells all lined up along the length of the muscle, and these muscles can shorten a long distance. Here's the example of the sartorius muscle going all the way from the anterior superior iliac spine of the hip across the thigh and to the medial side of the proximal tibia, and this muscle can flex the hip and flex and rotate the hip, then flex the knee and rotate the hip all at once. But it does it with a very low amount of force. That's not an action that we do with a lot of force. So we have a long parallel muscles with the cells all lined up, but a few number of muscle cells within there, a very small cross section across the muscle cells or the motor units, meaning we get a muscle that has a long lengthening distance, but with a very low level of force. Interestingly, soccer players who do this sideways kicking action with a lot of force sometimes get a very thick sartorius muscle that you can definitely see in the front of their thigh. On the other hand, let's look at a muscle that, like the gastrocnemius muscle on the back of your thigh, that pulls up on the Achilles tendon and pushes your foot against the ground with every step you take. It's a very short distance, so we don't need a lot of lengthening, but we need a lot of force out of this muscle. And so we have a lot of what we call pinnate muscle cells. All, instead of running straight up and down, they angle in, so you get even more motor units or muscles if you cut across there, and they come in from both sides of the muscle. And so we have a lot of motor units within a large cross-sectional unit, but it's a relatively short lengthening distance because it just has to pull up a little bit on that Achilles tendon. And it actually, the gastrocnemius muscle works together, two heads of it work together with a third muscle, the soleus, to form what we call the triceps surae, a very powerful calf muscle at the back of your leg that gives you a high amount of force, but a relatively short lengthening distance. So just to summarize, we get long, skinny muscles with a great lengthening distance and a low level of force because of the small number of motor units, but the long number of parallel muscle cells and sarcomeres. And on the other hand, we get these relatively short pinnate muscles that have a high force and a relatively short lengthening distance because the cells are very short in length, but they have a very large cross-section with a lot of muscle cells packed in there. Okay, finally, we want to take a look at how we really get smooth and fluid joint movements from these muscles, because we've been pretending so far that if we look at one of these muscles, it's almost like a robotic thing where the force direction is always going to be pulling in on the ends of the muscle as the cross bridges try to shorten all the sarcomeres and the muscle shortens up. And so we always have a force direction coming in, wherever that muscle is situated. And so it would be, if we're trying to, let's say, move our elbow joint like a robot, the idea is almost robotically we would get, oh, the biceps muscle activates and the elbow flexes. And then the triceps muscle on the back of your arm activates and the elbow extends, like these movements indicate. But in reality, our movements are not like that. We get very smooth and fluid joint movements because the muscles never act alone. There's always an antagonist muscle stabilizing the joint on the other side and allowing for those smooth movements. So the reality is much more subtle. When we flex our elbow, both muscles are going to be active. When we extend our elbow, both muscles are going to be active in the following way and with the following vocabulary to describe it. As we flex the elbow, the biceps muscle wins. It's what we call the agonist muscle in concentric activity, meaning the biceps muscle shortens and the elbow is pulled up this way, but to stabilize the joint and allow for smooth movement, at the same moment the triceps muscle is active, it's trying to pull in, but it is an agonist, an eccentric activity because it is actually lengthening as the joint flexes. So the biceps is concentric, shortening muscle, while the elbow is flexing, and the triceps is the eccentric lengthening muscle. On the other hand, the roles reverse when we extend the elbow. Now it's the triceps muscle that is actively shortening. It's the agonist in concentric activity, while as the biceps is the antagonist in eccentric activity. So just remember that the muscle force is always working to shorten, but whether it's concentric or eccentric, depends on whether the muscle is shortening or lengthening. So in summary, when we're flexing the elbow, the biceps muscle is shortening. It's the agonist muscle undergoing concentric activity, while the triceps on the backside is helping to stabilize the joint as the antagonist in eccentric activity. They reverse roles when we're extending the elbow, and now the triceps wins as the agonist muscle that's actually actively shortening in concentric activity, and the biceps muscle on the other side is stabilizing the joint. It's the antagonist undergoing eccentric activity. So that's an overall view of how we get smooth and fluid joint movement through the mechanics of muscle action across the joints from big picture anatomy.